So this is separation by precipitation. In this problem, we're going to take a solution that is both 0.100 molar indium plus 3 and 0.100 molar lead plus 2, and we're going to separate, as that says there, it should say separate, by precipitation with the sulfide ion. So we're going to add sulfide ion to this and try to separate out the indium and the lead. Okay, so the reactions that we have are indium 2s3 in equilibrium. That's a solid with 2 indiums plus 3 and 3 sulfurs minus 2. The KSP expression is equal to the concentration of indium plus 3 squared times the sulfide minus 2 concentration cubed, and that KSP is equal to 4 times 10 to the minus 70th. You're going to have to follow along with this problem. It's going to be long and involved. You need to be writing this stuff down or you'll never keep track. The other equilibrium is lead plus 2 with sulfide, lead sulfide, interacting to give us Pb plus 2 plus sulfide minus 2. The KSP expression for this one is equal to the concentration of lead plus 2 times concentration of sulfide minus 2, and that KSP is equal to 3 times 10 to the minus 28th. So this is one of the rules you have to know. Generally, if the KSP is smaller, which it is right here, the KSP is much smaller than that for the lead sulfide, you can take the smaller one, but it's not always the case. If the stoichiometry is not the same, and the stoichiometry in this case is different, if the stoichiometry is not the same, and it's not, it's 2 to 3 here and it's 1 to 1 here, then you have to calculate which precipitates first. So that's the first step, and I'm going to slide this up. So step 1, determine which ion precipitates first. To do this, we'll just calculate the concentration needed to start precipitation. Calculate the concentration of sulfide minus 2 needed to start precipitation. PPT is my symbol for that. Precipitation of, let's do the lead first. KSP equal to concentration of Pb plus 2 times concentration of sulfide minus 2. And I know the concentration of lead, it's 0.100. So the concentration of sulfide needed to start precipitation will be the KSP, which was 3 times 10 to the minus 28th, divided by the concentration of lead, which was 0.100 molar, and that gives us 3 times 10 to the minus 27 molar. Now I do the same thing with the indium. Calculate the concentration of sulfide needed to start precipitation of it, of the indium plus 3. Okay, and so same thing, KSP for the indium is equal to the concentration of the indium plus 3 squared times concentration of sulfide minus cubed. Okay, and so when I do that, I get the concentration of sulfide minus will be equal to the cubed root, or the KSP, divided by the concentration of indium plus 3 squared, and that is going to be the cube root of the KSP for indium is 4 times 10 to the minus 70th divided by 0.1 squared. That's concentration indium and the cube root of that. Okay, let me see what that is. That gets me 3.41 times 10 to the minus 23rd. Okay, so I have this one and this number. Clearly, that's a smaller amount of sulfide. 10 to the minus 27 is smaller than 10 to the minus 23rd. So the lead precipitates first. I'll make a statement to that effect. Pb plus 2 precipitates first because concentration of sulfide needed to start precipitation is less. All right, so now I got to go in and do the second step. Okay, step 2 is calculate 99% removal. So let's write that in. Step 2, calculate 99.99% of lead gone. You can rough it out like that. So what I'm calculating is what amount of lead is in there when 99.99% is gone. So that will be the concentration of lead given is equal to 0.100 molar. So 99.99% of that is 0.100 molar. And the easier way to do it is 0.01 over 100. That would be the amount left, not the amount that disappears. And that'll give us 1 times 10 to the minus 5th molar. So we're going to use this definition of 99.9% gone unless otherwise stated in the problem. So now that I know that that's the concentration of lead when 99% of it is gone, right here, I can go to step 3. So step 3 is calculate the concentration of sulfide when all the lead is gone. Now remember what our definition of all the lead is gone. It is 1 times 10 to the minus 5th molar. Okay, so I use the KSP again. So KSP for lead, KSP equal the concentration of lead plus 2 times concentration of sulfide minus 2. And I know what the lead concentration is, and I know the KSP. So the concentration of sulfide minus 2 when the lead is all gone is equal to the KSP divided by what we say is the concentration of lead that is all gone. Okay, the constant, which is this 1 times 10 to the minus 5th. Okay, so the KSP was 3 times 10 to the minus 28th, and the concentration of lead was 1 times 10 to the minus 5th. So that's going to give us 3 times 10 to the minus 23rd molar. That's the concentration of sulfide over here when all the lead is gone. The definition of all the lead gone is 1 times 10 to the minus 5th. That's a hang-up students have, okay? It's just our definition. Remember, you can never, ever remove everything. We have to define what we mean by all gone. It could be 1 part in a gazillion. Right now, it's 1 times 10 to the minus 5th. Okay, I'm going to move up, and we'll start on step 4. Okay, so we're going to go step 4 now. Step 4, method A, is compare Q for indium sulfide to indium sulfide's KSP. Indium sulfide. That's what I'm after here. The KSP for indium sulfide is 4 times 10 to the minus 7. Now, to calculate Q, Q is equal to the constant, same expression, indium plus 3 squared times concentration of sulfide minus 2 cubed. And I know the concentration of indium I have in there right now, 0.100 molar, and I square that. And the sulfide is 3 times 10 to the minus 23rd. This is the sulfide concentration that gets rid of all the lead. This is the lead concentration if none of it's precipitated. Now, in this case, I get Q equal 2.7 times 10 to the minus 70th. Now, Q is less than K, so K is 4 times 10 to the minus 70th up here. So Q is less than K. So the rule is if Q is less than K, then they're separable. If Q is greater than K, then it's going to precipitate out with the lead, not separable. Okay, we'll do step 4, method B. Step 4, method B. I'm going to calculate the allowable concentration of indium plus 3 when all the lead is gone. And if you remember, that is a concentration of sulfide equal 3 times 10 to the minus 23rd. So the KSP for this, KSP is equal to the concentration of indium plus 3 times concentration of sulfide minus 2 cubed. And so the concentration of indium plus 3 is going to be equal to the cubed, square root of the KSP, 4 times 10 to the minus 70th, divided by the sulfide concentration, indium plus 3 squared, sulfide minus 2 cubed. So I'm dividing KSP by the sulfide, which I know is 3 times 10 to the minus 23rd cubed. And when you do that, you get 0.1217. That's how much indium can be in there before it will start dissolving at this concentration of sulfide right here. So it turns out that that's larger. The allowable concentration of indium plus 3 is equal to 0.1217, and we have concentration of indium plus 3 equal 0.100 molar. Therefore, it's separable. This is not going to precipitate out. Now, one of the things about this last method is you may get an allowable concentration that is ridiculous, like 1 times 10 to the minus 10th molar, which is never going to happen. Other things will happen before that, okay? So you don't really worry about that. When you get something like that, you're like really separable, all right? Okay, good enough. So you'll have to be able to do this. When you do it on the exam, I expect you to take your time and separate it out and label each step. Otherwise, I can't follow it. There's multiple ways of doing this. There's even other ways. And if you don't say what you're doing, I can't follow it. You can't get credit.